Hi everyone. So I'm going to talk a little bit about the fuel cycle development and the deployment perspectives that we have at Moltex. As said, I'm the project director of our WATTS project, which is the project to develop our fuel recycling plant. Which WATTS is Watts Disable Salts. You can't be in nuclear without an acronym, it seems, and Moltex has definitely embraced that. So I'll say a little bit about what Moltex is. I will talk briefly about the SMR-Emerging reactor that we're developing because I'm only interested in it because it's what I will be making fuel for. Then we will talk about the Watts fuel facility, talk about what our upstream and downstream requirements are and how we see ourselves fitting in the broader fuel cycle, and talk a little bit about how we hope to help change the world, as everyone here does want to do. So Moltex has been around for a few years now. It was founded less than a decade ago, and some of the key patents granted then. It was a few years ago that we established ourselves in St. John, New Brunswick. New Brunswick Power is a local nuclear utility there who's provided a lot of support for us, helping us to develop our concepts and advance ourselves. Our presence in New Brunswick has been very helpful for us and their cooperation with us. In the more recent years, our team has been growing, both in Canada and in the United Kingdom. We're focusing on developing our design and the underlying science that supports it through R&D, and also developing stakeholders and supply chain options. We've gotten some major investments from established nuclear companies, and we were the first sort of nuclear crowdfunding instance in that time frame. But you can see we've gotten Canadian government support. We've gotten money from Ontario Power Generation. Overall, we're talking about $50 million in funding that we've received, US, I should say, from New Brunswick Power, Ontario Power Generation, the Canadian federal government, etc. We have put our reactor design through the first phase of Canada's Vendor Design Review Program, and we're preparing to enter the second phase pretty soon now. We've also formed a strategic partnership with SNC-Lavalin. In fact, I am one of the fruits of that program. I've been working with Moltex for more than a year now. It was only in the last few months that my role expanded to be the project director of WATTS, but I'm there on a secondment from SNC-Lavalin Nuclear. So I won't spend much time on this slide, but everybody has to have a pretty picture of their reactor, I suppose. We, similar to what we just heard about for Natrium, have what we're calling grid reserve, which is the ability to have output flexibility while operating the reactor at full power to support load following type activities. There's an SMR-Emerging and the WATTS facility, and that's the package that we would propose delivering generally to existing nuclear sites. So what's the reactor that I'm making fuel for? The SMR-Emerging, it's a high temperature molten salt reactor, 300 to 500 megawatts per unit. Our first unit will be at 300 megawatts, part of the overall plan for scaling up. We use recycled nuclear fuel waste as our fuel without removing the transuranics. So the recycling that we do at WATTS is a little bit different than traditional reprocessing, in that the transuranics stay with the plutonium when we do, but we do extract the fission products. I want to make sure I'm on the right slide here. There we go. We can produce grid scale power and high temperature heat. The idea is this might not only be an electrical producing facility, it can be used for other purposes and has a small footprint. The important thing to think about is that in general we're talking about placing these on an existing nuclear site. So when you talk about our upstream fuel supply needs, what we need is a repository of spent fuel. So an existing nuclear power plant that has spent fuel in its ponds or in dry storage on site, that's where we want to add a WATTS and an SMR-Emerging. You could think of our whole proposal as a sort of a midlife upgrade for existing nuclear power plants that also adds significant and better load following capability to the facility. And because we are using that spent fuel through SSRW and burning out a lot of the plutonium, we dramatically reduce the costs that should be expected for the overall waste disposal for the whole proposition. And that's a part of our whole economic argument, is that those sinking funds don't need to be as big as they would be without SSRW and Watts. So our Watts facility is a much simpler process than is in a conventional reprocessing facility. We've got a picture here. Granted, the one on the left is a real facility and the one on the right is the one that we're developing now. But our whole vision is of a facility. You can have one at each nuclear power plant, each site. Its biggest job would be producing the startup core for an SSRW, and then would have the smaller job of continuing to reprocess fuel. The cost proposal for this Watts facility is in the low hundreds of millions as compared to several billion for a traditional reprocessing facility. And it's important to note too that for our facility, if you know, from a reprocessing perspective, the sort of safeguards level of concern is much less because of the fact that, as I noted, we're not taking the transuranics out of our fuel. It makes it much less attractive from a proliferation perspective, or much more unattractive from a proliferation perspective, however you want to put it. And you know, if somebody wanted to do something untoward, they would still need a separate multi-billion-dollar facility to process what we produce as fuel. So to give you an idea of, at a very high level, what we're doing, we all know this, that most of the spent fuel that we generate is uranium and circuloid typically, which is not particularly difficult. It's just that it's all mixed up with these very highly radioactive fission products, as well as plutonium and transuranics. Our process is to extract the important parts, make our fuel salt, and put it in SSRW for our first load. And then there's another subsequent parallel stream where we can take our spent SSRW fuel, similarly process it, top it up with a small amount of additional fuel from the reactor that's supplying the original spent fuel, and on we go. One of the things that I should maybe emphasize is we're planning to roll out Watts and SSRW in Canada in respect to CANDU reactors. So if you think of that spent fuel as the ore that we're using a particularly low-grade ore. You know, as everyone's probably aware, CANDU reactors are naturally uranium fueled. Their burnup is low. The plutonium content in the fuel is quite low. It's around 0.3% perhaps. So our sort of pitch is that, you know, if we can make it there, we can make it anywhere. If you can extract the plutonium from spent CANDU fuel and successfully make a fast reactor fuel that we're talking about when you're only at 0.3 weight% in your fuel material, using more typical LWR fuel should be a piece of cake. So, you know, it's really important to recognize that we don't require HALEU, we don't require any other, excuse me, nuclear material other than spent fuel that's already on the site where we're planning to build our facilities. And this is an important part of our whole picture. We think that the fact that we're not requiring other materials like that, and we're making a contribution to something that reduces the need for a DGR, promotes a recycling sort of concept, really helps with the social license, not just with the general public, but particularly in a country like Canada, where there are Indigenous peoples whose rights have to be respected, and whose input on the environmental impact of solutions is very important. Being able to present them with a solution that achieves these kinds of things is very important to gaining their support, which is critical for us. So, you know, we did a survey in 2021 that showed that in the province of New Brunswick, where we're working now, 89% of the population of New Brunswick think it's important to recycle nuclear waste that's already stored at Point Lepreau, so that it can be used to generate clean electricity, which is exactly what we're talking about doing. You know, we use this material, we get something out of it now instead of storing it away for future generations, and the economics support this working out and being a paying proposition. So the last slide I want to give you is why we hope to be able to take over the world, so to speak. We're starting out in Canada, where the existing amount of spent fuel would be enough to support a half a dozen SSRW reactors. And we would envisage the idea of a Watts facility at every one of the nuclear sites there. Now, many sites in Canada are multi-unit sites. That would imply a somewhat larger Watts. But that's how it's workable. When you look at the amount of spent fuel that exists or will exist by 2040 in other countries in the world, you can see we could have 22 in the States, we could have dozens in Europe and across the world. Now, as we all here hope, nuclear grows in the future because we have to do this to battle the climate crisis. The prospects for SSRW only do as well. Like I said, I think that there's a lot of attraction in the idea of leveraging an existing site, places where there's existing licenses that have to be modified. You're adding another nuclear facility, let's not kid ourselves. But still, in general, you'll have a place where there's already often local support as well for nuclear power, instead of selling a community on a brand new facility. And at the same time, from a business perspective, like I said, the idea of a midlife uprate that also adds significant load following capability and reduces your spent fuel obligations for a regulator is a proposition that we think can make a big difference. And overall, we'd be talking about, we hope, worldwide, 120 gigawatts of electrical production being fed by SSRWs that are fed by Watts. Thanks, everybody.
Okay, thank you very much for attending. I'm Sander de Groot, representing Thorizon, which is a startup company from the Netherlands. This is the first time we are presenting ourselves to a grand audience, so you have the scoop. We are a very small company and just starting, and I will try to explain what our plans are and what we are going to do and why. So first of all, and I hope that everybody is aware that energy poverty is a major issue worldwide. We are facing an energy crisis, and also we are in the midst of an environmental crisis that we need to resolve. And this is not an easy task. It's a huge puzzle to make. And we also believe that new technologies will be needed to be able to solve that puzzle. And that also includes nuclear. So in this presentation, I intend to explain what Thorizon plans to do, how we plan to do it, and give you a bit of an insight in the technology option that we are developing. So Thorizon started at NRG. NRG is the Nuclear Research Institute in the Netherlands, operator of the high flux reactor, which is and produces the largest share of medical isotopes worldwide, but also operates or executes a nuclear research program for the Dutch government. About 6 years ago, I initiated a molten salt reactor development program at NRG, and we did some irradiations on molten salt in our reactor. It's still continuing this program. And during this program, we came up with an idea on let's look at molten salt reactor issues and look at an option how to maybe facilitate and fasten the development and deployment of molten salt reactors. And we thought, okay, let's build a reactor out of individual loops. And by qualifying one loop, you're qualifying a reactor. And this was the basis of a new concept, which we would like to develop further. And NRG agreed to that, but not within NRG. NRG is a research institute, does not have the capability to develop a reactor. So we got agreement to develop this outside, and this is how Thorizon was founded. So the founders are, for you on the left, these very handsome persons. Well, so Lucas joined the molten salt reactor program 6 years ago, And together with myself, we came up with this concept and developed this further with a team of 9 experts that were highly motivated to look into this. And while we are developing it, it became a stronger and stronger concept, and we saw more and more advantages of what we came up with. Molten salt reactors have many possibilities, can develop in all kinds of directions, but we developed our first mission, and that is to support nuclear implementation, to reduce long-lived waste and safely produce lots of high-quality clean steam. And steam, energy of course, but I will explain later. Okay, molten salt reactors, is it a future or a fiction? That was our question at that time. Molten salt reactors have a huge amount of advantages, potentially. It is a fuel and a coolant combined in a low pressure system, lots of opportunity for passive safety, and also lots of opportunity for very high neutron and energy conversion efficiency. So basically you could produce, you could close nuclear fuel cycles. And this is also why thorium has been attributed to molten salt reactors specifically, because of this high neutron efficiency that can be achieved. Also, walk-away safety can be achieved in the system if it is well designed. And the energy cost could become really low, because you lose a lot of additional safety and redundant safety systems, and also because you make very efficient use of resources and minimize waste. If you translate that to a more general term, you could say that a molten salt reactor could lead to nuclear circularity. I mean, very efficient use of resources and minimization of waste. Safety beyond doubt, and affordable energy for all. And these 3 items we think are key, because this is where the public interests are. And if you do not meet them, nuclear has a weak future, we think. And maybe just to extrapolate on this a bit, in my 20 years at NRG, I've seen the nuclear renaissance coming up and going down and coming up and coming down. Of course, before 2011, there was a nuclear renaissance, but the Fukushima accident clearly blocked that very efficiently. Of course, now there's a bit more realism about what nuclear safety is all about. But now you have a concern about the costs. Now we have an energy crisis looming, so now the costs are less of an issue. But I would like to remind everybody that, in my view, nuclear circularity, so to make efficient use of resources and minimize waste, is a key concern of the public. And you need to take it into account in any nuclear scenario. Because if you start with nuclear, you do it for 80 or 100 years, and you need to have a good idea on how to resolve things that relate to future generations. Okay, but that's a nice story, but what about the challenges? Because if molten salt was so easy, they would already be there. There are key challenges, and I've summarized this. There are more challenges, but these are the key ones we think. And that is material degradation to the harsh environment in a reactor. It's very complicated to prove that in a molten salt reactor environment, your materials will withstand these conditions for decades. It's basically impossible, and this is also why we think that molten salt reactor development has been postponed, because this was seen as an unsurmountable issue. Additionally, there is multidisciplinary complexity in the core. There's flow, flux, chemistry, all combined in this system. And of course, the experience on molten salt reactors is limited. A reactor has been operated in the 70s, but after that nothing was basically done. These are really significant challenges to bring molten salt reactors into reality. And as long as these are not solved, it will remain fiction. So from our perspective, from Thorizon, we aim to tackle these issues by maximally exploiting the benefits of molten salt and try to convert these issues into solutions. So we have made a very practical design, driven by nuclear experience. So we look at containment, we look at replacement, and from that we came up with a concept that looks quite different than the concepts that I've seen so far. And of course to use long-lived waste to create clean energy as a first justification of this system. But on this technology basis, a lot more development is possible. This is also where a key benefit of molten salt reactors are. Once you have the technology basis, you can develop it in all kinds of directions. And in this way, we want to avoid MSR staying a fiction, but giving it a future. So the concept that we have developed is quite different than what we have seen so far. We have decided that maybe the best way to approach it is to come up with a compartmented core, a modular core, so a core that is not a large vessel filled with salt, but consists out of individual modules that form their own containment, double containment actually. So these integrated, these modules are integrating a heat exchanger, dump tank, and a core section. So the top part of these modules, as you can see in between the lid and the bottom part, the top sections form the core, and the bottom parts are subcritical. Also, the modules itself are subcritical. And only when the salt is pumped upwards and the modules are placed close together in the configuration depicted below, you have a critical configuration in the top. And as soon as the pumps stop working, the salt drains and the system becomes subcritical. So we have relatively small replaceable core components, each of them with containment. No salt goes in and no salt goes out. And we also have no large vessel. We have a radiation shield, but no large vessel. We think to have this modular core, so one module basically is representative of the whole core. This facilitates reactor qualification and can also allow upgrades later on. And these modules can be produced off-site, or are produced off-site. Basically, when there is no module in the system, there is no primary system in your plant. So the whole plant is basically conventional. And only when you introduce the modules, you have your primary circuit inside. So in the configuration that we have selected, we can convert about 30 to 50% of light water reactor plutonium in a 5 to 10 year cycle. And this 5 to 10 years is determined by the materials. No new plutonium is generated because we add thorium to the system, so we have no uranium. The system has a negative feedback, passive safety, passive cooling in the station blackout scenario. And this was also evaluated by Tractable Engie, and also our calculations were checked by CNRS, and it was all successful. So this is a system that already on its own as a waste burner has an interesting perspective. But after realization and commercialization, we think the technology can be developed further towards closing nuclear fuel cycles, be it thorium or uranium-plutonium fuel cycle with a fast spectrum option. The technology basis can be the same. So where are we now? We are past our first phase. So we have a concept. There are no showstoppers identified. And we have found financing investors that want to invest in our technology. And we closed the financing round this month. We have 6 investors, 3 private, 2 regional funds, and 1 government fund. And they're all Dutch. Their funds will support the coming 3 years, where we focus on de-risking the concept and come up with a final design. So we want to grow the organization and generate this final design by analysis. We will do experimental code validation to make sure that our thermohydraulics are correct. And we also initiate and execute a core material irradiation program. So the materials that we have selected for the core, we want to irradiate to demonstrate that the lifetime that we foresee can be met. And also in parallel, we secure the supply chain and industrial participation. Because that's what we want. We are a small company, so we will need to partner. It's the only way to proceed, and we need to collaborate. We are setting up, and have done so, we already have about 20 partners involved, of industrial and MSR knowledge partners, and developed a consortium called Mosaic, Molten Salt Innovation Ecosystem, which we are developing now in the Netherlands, but will expand. And this is a collaboration of institute, universities, industrial parties, and also Orano is involved. The aim of this consortium is to speed up the development. We are currently looking at the plan to have this reactor up and running in about 14 years, 14 years. With these partnerships, we can accelerate the development with the aim to realize the system within 10 years' time. So that is our goal. And in this way, we think that we can contribute to nuclear development. Again, I would like to stress that dealing with the resources and dealing with the waste is a very important part of a nuclear future. And we hope that Thorizon will contribute to that. So thank you for your attention.
Okay, got the presentation, so that's a win. Good morning, everybody. Good afternoon. Pete Pappano with X-Energy TRISO-X. Let me give you kind of a little bit of a background on the company. So X-Energy was founded in 2009. Our headquarters is in Rockville, Maryland. In 2009, we had about 3 employees. Now we have over 300, and we keep growing. You can see there, $1.2 billion funding secured through Ardp, Advanced Reactor Demonstration Program. Fellow colleague talked about Ardp, heard that on this panel, and then again, I think one of the first panels of the conference talked about that. So, you know, Ardp was actually 3 tiers. The first tier was demonstrating an advanced reactor, putting power to the grid. TerraPower, Natrium, and X-Energy were selected for that. I'll be talking a lot about TRISO-X and fuel because the project for Ardp for us involves building a plant, a 4-pack reactor at a customer in Washington State, but also building a fuel fabrication facility, commercial facility that we call TRISO-X Fuel Fabrication Facility, or shortened to TF3, and that's really my role in the whole universe of the project. Like I said, the headquarters Rockville, Maryland. TRISO-X headquarters is transitioning to Oak Ridge, Tennessee, where all of the fuel work on the project will begin. So X-Energy has a number of offerings, products, if you will. Flagship is the Xc100. It's a 200 megawatt thermal, 80 megawatt electric, high temperature gas cooled reactor. It's a pebble bed. Takes advantage of UCO, TRISO fuel. UCO is actually a mixture of UO2 and UC2. Department of Energy has poured $300 million or so into the fabrication, irradiation, and qualification of UCO TRISO. So that's a good example of the U.S. government addressing a long lead item for a company such as ours, which was fuel qualification. TRISO particle at the level is qualified now due to that. Because of that program, we stand on the shoulders of the folks that did that to produce it on a commercial scale for Xc100. TRISO-X, that's, like I said, I'll talk more about that in detail. That's my company. Proprietary version of TRISO, it's kind of the same specs, same manufacturing specifications as UCO TRISO developed by DOE, but just made with you know, advanced, more modern manufacturing techniques. I think we have about 14 issued patents right now and about 30 under review. So the Xc100 plant, check. This is our pretty picture of the plant. It's a 4-pack. You can see sort of 4 reactor buildings attached to a steam generator. So it's 1 reactor, 1 steam generator. 4 is kind of the standard offering because it looks a lot like a coal-fired power plant at that range. It's about 320 megawatt electric. Like I said, takes advantage of UCO TRISO fuel. Now this, you can do process steam and electricity, so it's a cogeneration plant. The first customer there, Washington State, and specifically Grant County Public Utility District, is interested in electricity, but there is a large market for steam, process heat. That's actually why DOE got back into HTGR technology in the early 2000s. It was to attach an HTGR to a hydrogen production plant, so that would the steam or heat would feed the generation of hydrogen. So you have this kind of kill 2 birds with 1 stone approach with a pebble bed, or really any HTGR, steam and electricity. The reactor itself is about 220,000 pebbles per reactor. There's about 18 or 19,000 TRISO particles per pebble. But really, the 1 pebble is about a billiard ball size, 6 centimeters, only has 1 gram of uranium-235. So it's quite diluted, but maybe some advantages for spent fuel. Certainly, in making the fuel, we get advantages from the NRC due to that dilution factor. We'll talk about that in a little bit. But that's kind of what this reactor looks like going forward. Dissecting the pebble a little bit, you can see the TRISO particle that's in the front. A TRISO particle has a uranium-bearing kernel. In this instance, it's UCO. It can be other chemistries, UO2, UC2, can be UN, so it's a versatile, robust fuel form. Out from the center of the kernel, you have layers that all have a purpose. You have a low density layer, and then a silicon carbide layer that has a pyrolytic carbon on either side of it. So this is a very different approach from light water reactor, where the containment in a light water reactor is a big building, over the reactor site. Here, the fuel is the containment. These layers act in unison to retain fission products and radionuclides upon irradiation or during irradiation. Because of that, you can have a much smaller footprint. Because you have a much smaller footprint, you can sight in a lot closer to where you want to go. This is, again, the steam part. You don't have to be miles away from a customer that may want steam. So that's the promise of HTGRs, and it's all centered around the safety function of the TRISO particle. And then for added safety, the TRISO particle is encased in a pebble. The matrix of the pebble is graphitic. It's pretty standard stuff that you mine out of the ground, or you graphitize something like a petroleum coke. Scales there for size, 6 centimeter pebble, little TRISO particle. It's like a millimeter, like a BB. We say walk away safe. There's no active systems needed here. You have a negative temperature coefficient. I'm getting out of my swim lane here. I'm a materials guy. I grew up making graphite. That's how I got in this business. But my CNO says negative temperature coefficient, so that's what I say. So it heats it up and then it cools itself down because of the physics, the neutronics of what's behind there. We know HTGRs work. There's 40 plus years of data. The UK's had one. China has one now. Germany built two. So a proven technology. We make it. We have been making this stuff in significant quantities for years now. We call this the TRISO-X pilot facility. It's located inside Oak Ridge National Laboratory. We call it a pilot facility because it's just one line. There's like one piece of equipment or one station for each unit operation needed to make a pebble. But the scale of the equipment is commercial, meaning we don't need to make it any bigger. To meet demand in our commercial facility, we just replicate this equipment. So instead of, say, one TRISO coater, we'll have 6 or 8 or 9. And you can kind of grow in a modular fashion to meet the demand of whatever's out there. So this is X-Energy owned equipment, or TRISO-X owned equipment now, I guess, with TRISO-X employees. You can see them in the picture. Making fuel. Like I said, we've been doing this since about 2016, 2017. Because it's under Department of Energy regulations, we do handle HALEU, high assay low enriched uranium. So we have all the knowledge, processes, procedures, safety on how to handle it. We have made HALEU bearing material in the past. Let me, okay. So TRISO particle, and this is one of the reasons why TRISO-X was formed as a subsidiary of X-Energy about a year ago. TRISO particles can be used for many different things, and it doesn't even have to be a TRISO particle. It can just be a coated particle. You don't need to put all the layers on it. Some of the space applications or government applications that are in the top right there, where DOD and NASA don't really want all the 3 layers. They're not so much worried about containment. It's more about surviving heat. And not much burn up, so you can have a kernel that has more uranium but less layers around it. This is all material that we've made. That TRISO particle is one that we've made and then fibbed out a wedge. TRISO particles can be formed into a compact or a cylinder, that's on my left, or a pebble, which is on the right. This is not a rendering. This is actual material that we've made, and then we subjected it to 3D X-ray tomography, which kind of takes like a lot of slices of the material and then renders it back into a movie. The movie is nice, it's pretty, but you can learn a lot from it. You can measure distances between particles, maximum distance, minimum distance, number of particles. You can confirm exactly how many particles are in a pebble. And that's key in this kind of environment because, the uranium is in a kernel, but there's other stuff that's not uranium in the TRISO particles. So the way you control uranium is through the number of particles in your fuel element or your pebble. So knowing it exactly is key so that you can meet the specification and have the correct amount of uranium per fuel element, per fuel body. Now TRISO-X TF3, another image. This is what we're doing now in Oak Ridge, Tennessee. You can see an artist rendering here. Project overview, we acquired 110 acres in Oak Ridge, Tennessee at what's called the Horizon Center Industrial Park. It's about 500,000 square feet of processing space with kind of an office building attached to it. NRC licensed category 2. That's a big deal because in the US, there's 3 categorizations of fuel facilities. There's category 3, which handle material up to about 5%. They can go to 8%, but they're the 3 facilities that make standard UO2 pellets for light water reactor. Then there's 2 category 1 facilities, both owned by the same company, but there's 2 facilities in category 1 space. Category 1 allows you to go to high enriched uranium, but their customers are primarily government, U.S. Navy, naval reactor fuel, research reactor fuel. This slot range of HALEU, so up to 20% enriched, in the U.S. there is no facility that's dedicated just to HALEU. So this facility that we are building now, we are licensing now, is going to fill a void in the whole advanced reactor supply chain. And again, I want to emphasize TRISO-X is here for anybody that needs it. Xc100 is a customer. We have other customers. Category 2, having a category 2 facility is good for the whole industry. Because there is not one now, there are some unknowns with the NRC around how to regulate it. And just by definition, we're going to figure those out for ourselves. And then if anybody wants to come behind us. So, this was a big deal. DOE thought it was a big deal. I have a link to the presentation, or a link to that announcement here. There's a quote from that milestone announcement from DOE. TRISO-X will be nation's first high-assay, low-enriched uranium fuel fabrication facility. If you see in the right there, that's our regulatory director, Jennifer Wheeler, handing over literally the license application to her counterpart at the NRC, the program manager. It was a good day. It was an exciting day. The NRC joked that this was their first application in Category 2 space, so they didn't have a billing structure figured out for it. But they said, well, we'll get that done first thing, though. Don't worry about that. So other things we'd like them to be fast at, maybe they're not, but figuring out how to bill you, they got to that. So anyway, back to the facility. 8 metric tons uranium throughput a year. That's about 1 million pebbles a year if it was just making pebbles. Operational 2025. We submitted this license application in April of this year, so a couple months ago, anticipating about a 3-year review, so that puts us operating in 2025. Groundbreaking, later this year. So, so something new, something new being built in nuclear in the U.S. I think that's exciting. It's probably the first time, especially in a fuel area, for maybe 40, 50 years. This is the site itself. It's cleared. You can see there's a drone footage. We're about 50 people right now, but we're on our way to about 400. When this thing is an operating facility, you can see the initial team there, then a larger area. The area, of the site is the tree line, and it's like the furthest tree line. There's kind of a false one here in the front. We have been doing work on it. You can see some of the groundwater monitoring, geotechnical, all part of our environmental report that's gone to the NRC, collecting data for about a year now. So that's me on the lower right, a kind of a greenfield fuel selfie. How many people get to do that? So I wanted to put it in there. So, and then lastly, the city of Oak Ridge been very accommodating. We acquired this land for $0. $0 in a 20-year pilot program, which is payment in lieu of taxes. So, if we're trying to save money and get off to a good start, we did. The city welcomed us, and gave us this land, gave it to us to pay taxes, but other than that, no sale. Just one last, we made the front page of the Oak Ridger, which is the local newspaper. When we signed these documents, because the president, I actually got to sign away. So they'll come to me, I guess, when the taxes need to be paid, because I'm the signing authority. I didn't think about that before I signed it, but anyway, it was exciting news for us, exciting news for the community, strong community support. I just got to take 30 seconds on kind of an offside story here. The land that we purchased previously was being considered by a motorsports park. And this company was going to come in and build like a dirt track with like motorbikes, you know, and four-wheelers and things. And the city of Oecd people kind of rose up against it. They didn't want the noise of the dirt. Here we come with a nuclear fuel facility behind it, and they welcomed us. So it just kind of gives you an idea of the clientele in Oecd, very used to nuclear because of Oecd's National Lab, Y12 security complex. So it's been really good so far. We'll see how it goes. That's my last slide. We are hiring. I got to say that. Like I said, we're on our way to about 400 people. I was in some of the technical sessions earlier this week, some really impressive presentations, PhD students from CEA or whatnot. So look us up, www.xenergy.com, and that's all I got. Thank you.
Well, hello. So it's first off, it's a very fantastic panel to see. There are so many developers that are sitting on the shoulders of giants, developing exciting nuclear technology, and of course you too, everybody in this room. I mean, you've gone through a lot of work to be here and to stand up for nuclear and to develop nuclear technology. This is fantastic work that we're doing, everybody. But I'm gonna explain our story and what we intend to do in Estonia, which is in Europe, much more to the north than Reims. But yeah, we founded a company 2019 based on knowledge that we have to decarbonize. And I finished my PhD and I realized that the fossil industry, there's a big problem that is very capital intensive. And if you want to do capital expenditure, you need to have a certain ecosystem, foundations for investment. And with fossil industry, that is all crumbling. And that is one of the fundamental reasons, economic reasons, I as economist can explain why the capital flows are not going too much into the fossil fuels and why we are the energy inflation that we're seeing, observing. This is going to be a long inflation. And also, as a neighbor to this country called Russia, I can confirm you that the war is going to be a long war. It's not going to be a short, unfortunately. And this additionally means that price inflation that we see is going to be severe, and the crisis that we see in Europe, that the houses will not be heated, that the industries will not be served, and the prices are going to be very, very extreme in Germany, in France, and other places. It's going to be very, very problematic, and the high political attention will be paid to that. So that is the status where we are, and that we're the status where we have to provide solutions to the society. Yeah, I don't go to the background, but we are now about 20 people strong team, and we have lots of shareholders from Estonia, but we're very proud about Vattenfall AB and Tractable Henri being shareholders of FERMI Energia. We have partnered also with Fortum and Laurentis from Canada, and yeah, preparing our program for SMR deployment. So big countries, from our perspective, Finland is a big country, so they can do large reactors, and they can have the comfort of building the large reactor for 10 years or longer if they have chosen so to do. You have also good experience on long construction in Flammaville, but in small countries we can do only small reactors, and they have material benefits when it comes to financing privately, because the time is really important in business. For the governments, it doesn't matter so much, but for the states or business, it matters a lot. So our schedule, which we developed in December of last year, when we had the energy crisis of let's say, normal winter in Estonia, like -20 degrees Celsius, and the energy prices jump to 496 on a daily basis, and several existing fossil plants that were just, 45 years old. They were supposed to start, but they did not start. Gas plants, oil shale plants, they just didn't start, and they will not get younger in the future. So their availability will be even diminished in coming years, and a lot of coal capacity in Europe will be shut down, even if the CO2 price will be zero. It's just wearing of the material and running out of the mines, feed of like lignite mines in Poland and Germany. So our goal is really to achieve power generation by 2031, and therefore we have to focus on light water systems that are really licensable in Europe. We are now in a state where Estonian government has formed a nuclear energy working group that has prepared already the preliminary report to the government that will be submitted in September, and the final report by end of next year by mandate of the government, and based on that the knowledgeable decision can be made. And then we would be the first democratic nation this century to do so. And then we would at the same time go to the national designated spatial planning, the siting, and developing the detailed project solution on the site, and obviously prepare the construction license, so front-end engineering work, securing the land, and site preparations and so forth. There's some magic that who's professional in this business is probably seeing missing, so I will comment that privately. We are very glad that the nuclear energy support in Estonia has been steadily growing. We have measured it every half year. Of course, that matters a lot when it comes to politics. And in January of this year, the support level was, in comparison to other technologies, was 52% for nuclear and 50% for solar. So it's not so bad. But the context is that in January, Estonia gets 16 hours of sunshine. So a little bit understandable. So we'll have new numbers in August, but also the government surveys have shown that the support is quite good. The benefit of Estonia is that we're very close to Finland, so where the support for nuclear has been also steady. We are not copying anyone. We are learning from some experiences. Some introduction about Estonia. We are first on the PISA score on general education. We have most unicorns, like companies valued more than €1 billion, like five of them per 1 million nation. It's not so bad. Quite good digital economy. We are a free, open society, and like I said, close to Finland. So we have some things that are unique about Estonia. We are not afraid of challenges. We try to make things simple, focus on key problems, not all of the problems at once. So we are not necessarily using the normal nuclear approach on focusing on many problems at once. So which is, by the way, also very FERMI way, like being very effective at work. I recommend reading his biographies and learn from mistakes of others, which means in nuclear a lot of learning, frugality, not overspending, and work hard. Elon says 60 hours a week, so that is actually not a very good recommendation if you want to have stable family, but 50 is okay. And be humble. Now on fuel cycle, since we are in France, so we are setting certain criteria. Uranium has to be mined from NATO country, so no hanky-panky. So this means Canada. I'm very glad that there will be mining in United States. Apparently there is zero mining in Europe. Enrichment in lowest CO2 emitting nation, which means only France. for time being, because Quebec is, well, not pro-nuclear. Now from this week, the taxonomy vote is so important, but it has clear technical requirements in point 427 on the construction of new nuclear power plants. Point 4 says a plan for management of both non-radioactive and radioactive waste is in place, ensures maximal reuse and or recycling of such waste at the end of life in accordance with the waste hierarchy, including through contractual arrangements with waste management partners in reflection, the reflection in financial projections of the official project documentation. So that is why we are initiating studies with Orano how to couple Purax reprocessing and MOX fuel and vitrification of fission products into Orano universal canister, coupling with deep isolation borehole final disposal, given that we would have potentially 1,000 megawatt capacity in Estonia. Then the volume is small, and we would not do the mine solution in Finland and Sweden, but rather the borehole solution. And but we need to see how that couples with the universal canister and how it really can be done. So that is very shortly what we do, and maybe there are questions later. Thank you.
Thank you very much, Kalev. So now we have time for questions. I will start with one question, and then hand over to the audience. My question would be, what would be needed from the nuclear fuel cycle industry to support or even sustain the foreseen deployment of your technologies? So.
Hello. Yeah, for us it would be high assay low enriched uranium, number one. I have only two things actually. Kick the Russians out from all the supply chains, and second, more enrichment in Western nations. So those are two priorities from my angle. Thank you.
So in my talk, I talked about the idea that Moltex, from a technical perspective, all the fuel, all the stuff we want is already out there. We just want you to let us at it. But I would say that there is a related thing there. I think that in many jurisdictions, you need the right sort of policy framework or the right sort of way to engage. Often, I talked about the size of the market for us. A big part of the economic case for us getting into that market is the fact that, all of these utilities have put away so many billions and billions of dollars to support deep geological repositories that we think, they're heading towards a savings target that isn't necessary. But you need to figure out the way to help build that consensus that we can go another way. Moltex is not saying that you don't need deep geological repositories, but we are saying that they can be much, much smaller and that we can be leveraging this money. But that requires figuring out the right way to do that. That means building the understanding that this is a viable path, and then getting, the entities, usually governmental, that oversee the necessity for setting this money aside to recognize that this is a legitimate pathway.
From my perspective, and I'll leave the natrium fuel for Chris to address, but for the X100, as it's already being operated today, a couple of phases. Number one, it's just a scaling relative to what we need going forward with all these projects being announced. And number two, continued investment in understanding accident-tolerant fuel and LEU plus and other things that continue the value that we bring into light water reactors.
Yeah, and for us, we would like some plutonium salt, please. And but of course, I think what we would urge to do with nuclear industry is work together on our concept and the benefits it has So the modular concept could allow bringing modules to a processing facility loaded with salt, put it into the reactor, but also after irradiation, put it back and recycle the salt and make that a part of the whole recycling and reprocessing business.
Is it my turn? Yeah, I think others explained really well how much we need these new designs. There's no world where just one or two of us are successful. The addressable market is huge. I mean, all the models are showing that, on a clean energy grid in Europe or the US, or any country really, that it's optimal to have 20 to 30% nuclear. So there's room for lots of us to be successful, and in a way, our biggest competition is in each other, especially in the US and Europe. Some of the first pilot projects. And you got a real opportunity to demonstrate some of these plants in the 2020s and kind of earn that our credibility, and so that nuclear can present that 20 to 30% generation that we need. But if we don't, we could be crowded out with things that aren't as cost effective or aren't as good for the planet. So I think we need good, well-organized projects, and that's why we have great partners like Hitachi and Bechtel. And the supply chain is going to be a challenge. We're going to start with just one project each to demonstrate it, and then we're going to have to quickly ramp up. And HALEU was mentioned, high-assay low-enriched uranium. That's one supply chain issue. There's going to be others. It's one we're going to right now. The heat transport reactor to HALEU, as does the Xc100 And this first project, for our first quote, we're really working with the Department of Energy to downblend highly enriched uranium. But we need another source of HALEU, for our subsequent corridors and future reactors. And that supply chain doesn't exist in the U.S. right now. So the Department of Energy is promoting a strategy that the U.S. government gets involved in, placing some kind of large order for HALEU, by the way, separate bottleneck, given your post-Russian Ukraine situation. So, yes, we need HALEU, but there's going to be other supply chain issues. We're really going to have to succeed on these demonstration projects this decade to kind of earn the right to have that 20% of nuclear events. Thanks.
Thank you all. I will hand over to the audience for questions.
Good afternoon. Thank you so much for a great discussion, great panel. I'm Deanne Cameron from the Nuclear Energy Agency. So the first question was, what do you need from the fuel cycle industry? My question for you is two-part. We're an international organization. We're a member-driven organization, but our members are national governments from OECD countries. What is the one thing, if you had one key message for the national governments of OECD countries, so largely Western countries, something that you think you would really like them to understand that maybe they haven't been paying attention to, or maybe they don't understand as well as you'd like them to, what would that one key message be? And second part of the question is, if you had one ask, what is the priority action that you think Western countries should be taking to enable the success of the deployment of your concepts?
If I can start, thank you for the NEA question. I just participated in an IAEA around licensing harmonization. And I would say that that is one of the key areas that was attended by a lot of the regulators, NEA, NEI, WNA. So I'm glad to see that IAEA is harmonizing the harmonizers out there. But I think as we scale and we look at Western countries' technologies, whoever they are, it's going to be very key to be regulatory efficient there. And the second part of your question, just get it done. We've been talking for a long time, and I really hope we can move forward and get to the vision that we all share.
If I may, first off, maybe someone doesn't know, Diane Cameron is a giant when it comes to SMRs and nuclear. So the work that you have done in Canada, the first recommendation would be to any nation to do the same work that you have done in Canada as a government, as provinces and companies in collaboration. But coming to the licensing, I'm a fairly young person, but I've been talked, and also I think that's practical to go back to the future, well, back to the history, how in the 60s and 70s actually nuclear was deployed in Spain, Belgium, and also in France. How the American reactors arrived here and were treated by the natives. It was the licensing basis from the country of origin was very much accepted, and there was no bespoke designing to some imaginations, no ONR uniqueness, no kind of let's have this kind of welding, no let's have different kind of foundation. It was standardized design, and it worked. It's safe. It is safe. So the desire of some regulators to have their nose into redesigning the plants, this has to be kept in check. And we have to be quite demanding here that this is not best practice. This is abnormal, and we have to use the designs that have been deemed safe by very capable regulators. Thank you.
Yeah, so from my perspective, I think one of the messages is to countries, especially if they restart nuclear or start with nuclear, is that it is not something that you do by ordering a few reactors. It's much broader than that. The basis for nuclear implementation is a decision for policy for at least 80 to 100 years. And I think that countries should be aware of that. It also means that a lot more is needed, as said, than just ordering reactors. You need to have the knowledge base, the people, the regulator, but also, and that's of course in my interest as Thorizon, also perspective on innovation, improvement, and future perspectives on nuclear. And I think that perspective is important to maintain public support for nuclear. And if you make a decision for 80 to 100 years, you need that support for that amount of time, or else you are starting something that will end in a disaster. And I also think that innovation will attract talent, which is also desperately needed in the nuclear sector. It's an old sector. So you need these new people, you need that new talent, and they will be attracted by innovation, by new developments, by new perspectives. That's what they would like to work on. So I think there are two sides to this, and yeah, I think countries should be aware that this is not just a decision to order plants. It's a decision that for the next 80 to 100 years need to be taken into account, including innovation. I forgot your second part of the question, but it's on what action? Yeah, of course, if you look at 80 to 100 years, it will take time to think about that period of time and what would be needed. And the action would be, of course, there is now a short-term action that you need to do. If you want to order a reactor and deploy nuclear quickly, it will be light water reactors. There is no way around it. And why not? Existing technology, proven technology. But please keep an eye on the longer perspective. Nuclear is a long-term thing. And take that into account in your policy with regards to knowledge development, innovation, people development, and also on the regulatory side. Do not forget about the future, I would say.
I'd like to say everything I heard up here is like music to my ears. It's like I'm listening to my midnight grumblings to myself, articulated much better than I ever have. And I think a lot of the things here merge in together. I think that regulatory efficiency, the fact that in so many cases, the critical path in deploying a new facility is licensing, is problematic, right? But I think a lot of things that were talked about up here are part of the key to solutions. I think that one of the things is, in those earlier deployments, I think regulators were also deeply knowledgeable about what were then developing designs. And I think we need to sustain that, we need to, attain that level of knowledge in the regulators who are reviewing now. I'm not saying that regulators aren't knowledgeable, but they're facing a challenge, I think, of bringing their technology understanding on novel technologies up to speed in the same way. We're all facing this. It ties to the resourcing challenge we have of attracting talent. You need to have enough brains that are learning enough new things and getting it deeply embedded. But the last thing that I'll say, to actually say something different that I think that maybe governments need to do, is to really accept something that we heard down at the end of the line. I have so often heard the idea that new nuclear has to be an order of magnitude safer and an order of magnitude better than existing plants. I'm all for better. I'm all for safer. But there's an implicit message there that existing nuclear isn't safe. We have to, it's certainly true that we need to build social license. We need to reach out to the broader public who have concerns and fears about nuclear, and we need to help them to understand what is. But I don't think we achieve that when we tacitly concede that there's something unsafe about existing nuclear. I think that's bad as an impression that's out there. It's a wrong impression that's out there, and I think it drives needs that are inapplicable. There we go.
So I was just saying last night was the point of today's nuclear plants are very, very safe. Nearly all of them should see 28 license extensions, which in the U.S. and made a lot of that process. But then my answer to the question is really about talent. And this is something that I know OECD, the agency, is working hard on. Last week, Bill Wileman arranged the global commencement ceremony for all the graduating nuclear energy science and engineers last week around the world. And we felt it was so important to motivate that young group of people in this really tight labor market. When we asked Bill Gates to speak to the graduating class, and he did that virtually. Because we really need, a young, diverse core to help us with, these plants that are going to take, 7, 8, 9 years to build, and then the ramp up is going to be incredible. We're going to need even more universities with nuclear engineering programs. I can tell you the University of Wyoming, we're building our first plant. I'm working directly with the president of that university to help them prepare the Wyoming workforce. So thanks very much.
Any other question from the audience?
Thank you. So I have several questions. So the first one is that you said that the licensing review is on a critical path. Do you have the feeling that the safety authorities you're dealing with have the capability to handle the licensing of new technologies and several ones at the same time? And you have recommendations in terms of the processes that they need to change to achieve that? So that's my first question. The second question is, do you have the impression, because we've talked a lot about reactor designs, that the governments have the understanding that there's also a need for a fuel cycle? We talked about it, and that fuel cycle could also be on a critical path. And last questions for the ones who are working in Europe. now that we have the taxonomy recognition, what is it that we could do to engage with the European Commission to really get them to invest on new reactor designs and new fuel cycle processes? That's my 3 questions.
Yeah, I guess I'll start just because we are in the line. We are an applicant with the NRC for Part 70 Special Nuclear Material License Category 2 with the NRC. So is it critical path? Yeah, it is. Do we expect an expedited or efficient review? We think so. So, you know, the license application took the better part of 3 years and about $20 million. In that time, the NRC visited us about 24 times and saw the pilot facility that I showed. They were able to watch us make fuel. They toured the site that I showed. They have seen, they've been part of at least one design reviews of the facility. So we've tried to bring them into the process early and often to familiarize them with what we do, because it's very different from what they're used to seeing in an existing fuel cycle. We hope that this leads to a good review. So far, it's all been headed that way, to the point even that before we submitted the application, a fatal flaw review was offered by the NRC to see if we had missed anything fatal. We didn't. You know, there was some sort of indirect comments about detail here, detail there, but that was kind of like the teacher looking at your paper before you submitted it. So when we actually did submit it, you know, they have an idea of what's coming and who to send it to, so that they could, you know, more efficiently assign reviewers. And I guess, you know, so should it take 3 years and about $15 million is what we're thinking? I don't know. But what I do know is that if we were to expand to deploy to another Western world, this is kind of to your question, Diane, to another European country, I don't think it should take as long. You know, we've been vetted once. I would ask that the regulatory environment in the second country should be expedited, because it has been vetted by, you know, the NRC, one regulatory body. There is, at that time, there'll be operations, you know, to draw from. So I think, you know, again, back to the last question, licensing is an issue. Harmonizing it, I like that word, and making sure that, at least on the second time, you know, it shouldn't be critical path, because there's so much data now to work from.
I was the one who made the comment about licensing being often critical path. I'm not saying that that's an absolute blanket, but I'll make a comment about this that occurred to me as I was speaking. One of the things that I think that drives long licensing review timelines is the whole model that we have of regulatory review is something that we wouldn't want to apply in quality production of a product from a plant. I've talked to many people in manufacturer who are always against inspecting quality into the product, right? Wait till the product's there and then find out what's wrong with it and send it back kind of approach. This argues for a strong early engagement, but it also, the problem is what I sometimes see is that we do a lot of early engagement and then still have the inspecting quality of the product at the end. My personal feeling is that there needs to be a lot more of an embrace of the idea that the licensee has to be the one who is responsible for safety. And the regulator should not be responsible for confirming that every calculation is correct, right? Now, I don't think there's any regulator who actually does take that as their mandate, but I think the mindset gets a little bit more towards that. And I think we need to develop processes in the licensing where confidence is developed in how the licensee is meeting all of the requirements, right? And the regulators focus more on that than on the specific outcomes, because otherwise you end up doing everything multiple times that they can't possibly be efficient. That's a personal perspective on it. I'm not saying that I have all the solutions for exactly how to work that out, but if we talk about licensing harmonization, the licensing harmonization that goes to that sort of a thing, I think would have a lot of value in what we get out at the end, right, to help improve that timeline. you know, I've often heard regulators say that they don't want to be critical path, and I've seen many regulators, they have that as a very genuine desire. They're very, you know, focused on making sure they're fulfilling their mandate, which is making sure that everybody does things in a way that aligns with any company's regulations that are intended to make people safe, make sure the environment is protected, make sure all those things are taken care of, right? But they don't want to be the barrier. But I think it's all about how we get there.
I take, Valerie, your question's second part about the investment. First off, I think that beyond the taxonomy, European Commission is quite irrelevant. It's not investing. It's not American DOE or anything like that. I've worked in Foratom for some times, and I not worked there, but we have been members. So I don't have any illusions about any relevance of what the Commission does or does not when it comes to Europe. What matters is what we do as a business and how we, as a business, execute and start projects. I'm very pleased, I'm just going over the list of some nations that aim within next 10 years deployment of SMRs. That's Romania, Czech Republic, Poland, now Sweden announced Vattenfall clearly to deployment. France is a little bit slower, but UK also wants to have fairly quick deployment, and we are a little bit, within 10 years in Estonia as well in range. But in Netherlands, there is openness for nuclear, but in general, but what projects will be executed will be seen. But I think that when we look at the decarbonization challenge, then the countries like Spain, Italy, Belgium, Switzerland, Norway even, there are groups like that there considering. So essentially all countries except for Austria and Luxembourg should have nuclear in the future. You know, and if those countries deploy or those companies deploy, they will benefit from that, and their customers will benefit from that. And I don't think that the investment or the money availability, especially after the taxonomy vote, is a problem. If you're educated, well versed in the energy business, then you recognize that what is offered here, developed here, this is tremendous value. This is tremendous value. Okay, thank you.
Yeah, maybe I can add something, or I don't know if I think I will repeat others, but basically I think it would of course be absolutely great if the licensing on nuclear could be harmonized within Europe. It would help a lot. Also in terms of resources, I mean, regulators could, you know, work together on stuff, could actually be exchanged to countries to facilitate the whole licensing process. But that was also the case 20, 30, 40 years ago, and it didn't happen. And I think if you look at how the current EU taxonomy came to be, it's still a very large political struggle where one country wants this, the other country wants that, and to come to European harmonization will be extremely complicated, I think. I hope it would be the other way around, because it would help. I mean, so much double work, so much differences in, also for vendors to be able to sell their plants. So to have that harmonized would be, of course, great, but I think it will be complicated. The EU taxonomy and the decision that has been made now, I think, is mainly of importance for the financing of the plants. It will allow a lower interest rate for loans, and it will facilitate investment in nuclear to a very large extent, because it's the capital costs that determine the cost of nuclear, basically. So this EU taxonomy decision will play a key role there. But whether Europe will be able to go to harmonization of regulations, I think it will be very, to my pity, I think it will be tough. But we should aim for it, of course. And with regards to our situation, our planning is very long. So for us, the licensing is not on the critical path yet. But if our development would indeed accelerate to 10 years, it would definitely be on the critical path, and specifically at the beginning of the regulator, which needs to build up knowledge on this new type of technology. And that's where the challenge is. These people need to be there, and the knowledge needs to be there, and they need to be educated, and that will take a significant amount of time. And that's also a risk, because it's very difficult to plan and to control how much time it will take for a regulator to come up to speed with a certain technology, and then also define the regulations to be able to provide a license. So, challenge.
Excuse me. My name is Bjorn Peters, Chief Financial Officer of Dual Fluid, another future SMR vendor. We didn't touch too much about the financing issue, so us all together, we will need at least 100 billion or so in the next 10, 15 years to build up serious production, and most likely won't come from governments, so it will have to be private sector money. So are we doing enough? Is capital a scarce resource, or are we doing enough to educate the financial markets that this is a good investment opportunity and what the properties of this market is? Because most investors don't know us yet, and it's very good that NewScale did an IPO. That was certainly very helpful, but it's just one company and we need much more of it. So what is your perspective on this?
So FERMI right now is also publicly traded. We are not on a stock exchange, but there is an investment platform in Estonia where we have 1,243 investors that own right now 9.3% of the stock in the company. And we believed originally, and we raised through that 1.6 million last year. Our next stage is that we are transforming our company to public liability company, like from private liability company to public, which is a stock company. Then you're able to go to the stock market. Then, indeed, after Estonian, we make the knowledgeable commitment by the government. Then we are prepared to go to the Estonian secondary list not the IPO, but there is a first step is what's called private placement. And because IPO you do when you really need this big money for the deployment. So then when we would get into the stage of actually getting the license for the site, then this the moment where we need sufficient equity that justifies IPO in Estonia. In Estonia we have done the IPO, the largest IPO, last IPO for a green company, energy investment was like 200 million. They had 60,000 shareholders. I want to have more, much more. And I definitely want aim that FERMI would have the projects elsewhere than in Estonia, because we need much more nuclear. And I'm not very, but yeah, let's say existing utilities, especially utilities that have multi-energy, are competitive within their company with renewable and gas and coal and what have you, and then they are not investing sufficient management focus and time and intellectual effort into nuclear. That is very unfortunate, which is a great business opportunity for me. Thank you.
I would say I've attended a lot of conferences over the years, and it's mostly been a lot of my friends speaking on the same topics. And as of the last few years, it used to scare me to be in with a Wall Street person, but I've actually gotten along with them. And their interest level is really coming up. In Europe, a lot of private investors, industrialists are looking to invest. So I would say it's a positive trend for me and well needed, because we can't do it just with the government.
Maybe add one other thing. Of course, I think all SMR vendors and developers are facing that, the $1 billion problem, you might call it, right? Where do you get that money? I think we should remember, though, it's a drop in the bucket relative to global investments that happen, right? I think the thing, my personal thought is that the thing that we just heard about the increasing interest is, it's like how over the last decade, continued investments kept on happening in the stock market, and that was partly because returns and other things weren't that great, You know what I mean? Bonds were doing that well, and you know the interest you get in your bank account is negligible and all of that sort of stuff. So they called it TINA. There is no alternative, right? You invest where you can invest. And I think we're building the case. We're starting to realize that nuclear is a TINA investment, right? It's one of the few things that we can be doing to prevent really bad stuff coming down for all of us.
Thank you very much. I would like all of you to join me and thank our panelists for this very good panel.